the details on how shit works, and in this case, databases. So, Gabel.
Thank you. Yeah. Is it working now? Is it working? Oh, yeah, it's working. Brilliant. OK, hi. Hey, thank you very much. Good afternoon. It's really cool to be here. It's my first time in Rotterdam, the first time in this conference. I'm enjoying both a lot. I hope you are as well. Without further ado, we're going to be talking about databases today. It's a huge topic, so we're obviously not going to be able to cover much of it. My agenda for this talk is basically to give you a little bit of intuition about how databases work. And in order to do that, first we need to figure out what they are, what they're used for, etc. But to start at the beginning, every talk should begin with a good story. My story begins with a grumpy CEO that calls you in on your first day of work and tells you to make some money. Now, obviously, just a mission statement of making money is kind of routine for every software company nowadays. You need to have a better idea of what it is that you're going to be doing to make that money. So you have this whole organizational thing where you have your product manager, they tell you what the product is supposed to do and how. You have your chief architect, they tell you what the structure of the project is going to be like, what the basic technologies are going to be, etc. And you have your middle manager that makes sure you actually do what you say you do on time and on budget. Those were, of course, all lies. But ideally, at the end of a long-winded and annoying organizational process, you will have reached the point in your company lifecycle where you have a concrete product to build. You know what it is the product is supposed to do. You divided it into some kind of set of sane chunks. You have, your sprint plan or your minimal viable product, well-defined, hopefully. You're all set to implement the thing. And then you need to pick a database, because almost every product, ends up needing some kind of database. So how do you choose? Right? If you look at the database landscape, you have all of these options. Right? These are just a few of the common databases out there. And if you didn't already have working knowledge of any of them, you would be spending your days on Google and Stack Overflow and Reddit and Hacker News and all these things, asking all of the right questions and getting so much information and so many contradictory and confusing statements about which database you should pick that you might end up in this state, i.e. thinking that MongoDB is web scale. So really, as with anything else in this industry, and I kind of gave it away there, sorry, if you were to try and answer the question which database I should pick, and you went to your resident freelance consultant or what have you, what answer are you going to get? Classic. Annoyingly, it's also true. It really does depend. It depends on the context, it depends on the product, it depends on a whole host of things. So the statement, it depends, technically correct though it is not really helpful. There are too many different paradigms in this market, too many options, too many nuances of which option works best for which use case. And it really is overwhelming, especially if you're at the sort of beginning of your career or you don't have the right kind of mentorship. It can be tremendously overwhelming to pick the right product for your particular use case. But it turns out that you don't actually need to know everything. And although I'm jumping ahead a little bit, it also turns out that all of the practical, pragmatic choices you might make don't matter as much as you think. But we'll circle back to that. Let's begin with, at the beginning, how do you pick a database? So in order to do that, knowing a little bit can actually get you very, very far. And in order to learn a little bit about databases, the first thing, sorry, I almost forgot. A little bit of a disclaimer. I'm not a database expert. In 30 to 40 minutes, we're not going to be able to get into any meaningful depth on any of the 75 different angles of attack you could choose to talk about databases in. Right? This is a huge subject. We're barely going to scratch the surface. We'll simplify a lot of things, and possibly most crucially, I might be wrong. Right? Some of the things I might say on stage here are going to be flat out wrong, and that's fine. My ideal end game for this talk is that at the end of it, you will have at least a little bit of intuition about how databases work, just enough to know to separate the market into different categories of databases, and just enough to know how to Google for the next step and to deepen your understanding of this subject. So, beginning at the beginning, what is a database? What does it do? So going to the source of all human knowledge, Wikipedia, Wikipedia says, in computing, a database is an organized collection of data stored and accessed electronically. So that is a database. Fine, it's just a collection of data. More critically, though, what we care about is the system that orchestrates and manages, provides access to that data. In other words, the DBMS. The R in RDBMS just stands for relational. It's a particular type of DBMS. But database management system, that is the thing we're interested in. And what does a DBMS do? Any database management system effectively does 4 things in many, many different ways, but effectively it solves 4 problems. How to model data, so this is what in the traditional SQL world we might call schema. Data manipulation, so you have a description of the data and you have a database that is a collection of data. You need to be able to push data into the store. You need to be able to modify data in the store, remove data from the store. So basically the CUD operations in CRUD. Where does the R go? Data retrieval, right? That is another thing the database gives you. If you have a collection of data, you need to be able to at least in some way retrieve data from it. Ideally, you also want to have various powerful tools at your disposal, such as filtering and sorting and what have you, depending on the type of database. And finally, you have everything else, administration. Right? It's not enough to store the data and retrieve the data. You also have to be able to provide security, backups, snapshots, data retention, data compression, whatever else. All of the nice things that your database does for you that are not strictly store this and retrieve that, all of this gets lumped in this 4th category. And today, I want to mostly focus on the second thing, data manipulation. Because as it turns out, whatever database you use, whatever you use it for, unless it's strictly an in-memory database and you don't actually care about that data the second someone flips the switch on your code, you have to store the data somewhere. Right? There's a bunch of bits. They're going to have to be persisted to some kind of persistent storage medium for later retrieval. Without this, we wouldn't be having this conversation. There is no point to almost any database unless you're in a niche market without it actually being able to persist and store the data. So the obvious questions are, if you have a bit of data and you want to store it, where? Where does it go? And how do you store it? How do you model it on disk? How do you deal with all of the ramifications of having your data stored on what is effectively a non-volatile form of memory? So there's many, many, many different types of databases, and they fall into many categories. But one of the most critical, I guess you would say, axes by which you can actually try to separate databases from one another is the form of representation. So we're pretty much all familiar with the traditional ones, so that'd be relational stores, MySQL, Postgres, SQL Server, Oracle, which I'm having a very hard time saying with a straight face. Or you have the more sort of modern-day NoSQL-esque databases. So you have MongoDB, which is the first kind of popular document database out there. But you also have graph databases. You have things like Neo4j and Allegro Graph and a whole bunch of others. You have geospatial databases. So that's actually a feature in most other database systems, but you might want to do geographical searches. And then you have time series database. So who here uses Prometheus or Grafana or any of those tools? Right, you're all using a database. It just happens to deal with time series data, but it is effectively a normal database. So what I want you to, in order to simplify this equation, in order to actually make any meaningful progress on this subject, I want you to think of all of these as glorified key value stores. That is, at the same time, true and a gross oversimplification of the reality of it, but from strictly an academic perspective, if you will, you can actually implement any one of these data representations on top of a key value store. And in fact, many databases internally kind of work that way. Again, grossly oversimplified, but also kind of true. So we're going to treat all of these as key value stores. And in fact, if you think of key value stores, if you've modeled your data so that you can look up any piece of data that you're interested in just by virtue of having the right key, then we don't really need to talk about the value. All we care about is the key and how to store that key value pair, that tuple, that whatever it is, that chunk of bits on a storage medium, and then retrieve it. And that's what we're going to be focusing on for the most part today. Now, hearkening back to your university days or your initial days of playing around with computers, one of the first things that any budding programmer will end up dealing with at some point or other are binary search trees, because it's a very simple to explain, very simple to reason about, and very useful structure. Basically, what you do is, as data comes in, you keep it sorted in memory. You don't just have a pile of data that you then rummage through. You take the thing that you're given, you find it its rightful place in that sorted list of things, and then it's easy to find later when you need it, right? If you pay the cost ahead of time of pre-sorting the data as it comes in, then lookup becomes very, very cheap. Very simple idea. So suppose you want to look for that 5 within the tree. You basically had 3 hops, right? You start at the root node. You go left to right depending on whether the thing you're looking for is less than or more than the thing you're looking at. And then within 3 hops, you get to the 5. Not very interesting. What is interesting is that you get logarithmic efficiency at the price of doing some work ahead of time when new data comes in. Unfortunately, this is not a very useful structure for practical production systems, because you get a very limited branching factor, meaning you have a logarithm of 2 of how many items you have in your data set to get to any one item on average, right? A branching factor of 2 just isn't really great for practical computer systems. And more importantly, you get these pathological behaviors, right? Depending on the order in which data is provided to you for insertion into your binary tree, it is very easy to get into the situation where, in order to look up any value, you effectively have linear complexity, right? You have a linear number of hops with the number of items you have in your set, which is bad for you. So how do databases actually store data, right? Obviously, they're not using binary trees, but the principle of it is foundationally sound. The principle of it is something useful you can do when you store your data. What they actually use is some form of balanced trees. And it's not just this that they use, but we're going to circle back to the other options in a bit. What is a balanced tree, right? Computer Science 101. A binary tree is a tree structure that is optimized in such a way, it is constructed and it is managed in such a way that it limits the tree height. It tries to guarantee that for any given item within the tree, if you want to look up that item, you have an upper bound for how many hops within the tree you have to go through. And you do that just by limiting the height of the tree. If you have as many hops as you have, a height, basically, then you can't have pathological situations like we did a slide ago. And the reason you do that is essentially to reduce the write cost, because writes are still expensive. We'll get to that in a second. You want to avoid waste and fragmentation, but most importantly, you want to guarantee that the read performance is good regardless of where in your data structure the little piece of information is stored. So examples of balanced trees that you've all probably come across sooner or later in your studies or wherever it is, however it is you ended up in this profession, AVL trees, red-black trees, splay trees, all of these are examples of balanced trees. And the canonical balanced tree, the one that is used by virtually every traditional database system known to man, is the B tree. So a B tree is a tree structure, one that typically has many, many, many more items inside every node. It's not just one item inside of a node. It has n. It has n items inside of a node. Namely, it has between 0 items and a certain order of items within one node. For this example, it's just 5 items. No biggie. But crucially, what B node does, what a B tree does that a normal binary tree doesn't, is it tries to amortize moving of data and trade that off with storing data in a way that is efficient for lookups. So just to give you an idea of what that looks like, suppose we have this tree in our store, and we're not going to go into too much depth on any of these algorithms. Right? Suppose we want to add 26 to the tree. We go from the top. I hope you can see the little dot there. We go down because 26 is less than 82. 26 is less than 27, so we keep going left. We hit this leaf node. We want to add a new piece of data to the leaf node that we've looked up. But because we've basically filled up the last lot in our leaf node, that is the trade-off point. That is when the B tree looks and goes, I need to split this data up. Right? I need to trade off a bit of cost at the time of adding the data to my store so that lookups remain fast. The way it does it, it takes this whole block, takes the median item, that is 13, pushes it up, and splits up the block in 2. And essentially, recursively, that's how it works. A B tree takes in data, finds the relevant leaf node. If it gets what you might call overloaded, then it splits it up into further blocks, but it keeps those blocks at the same height, which means you have a tree that gets progressively wider, but retains a more or less fixed height, a logarithmically growing height, if you will. Now, why is this interesting? Right? This is really a kind of a brief 2-minute introduction into how B trees work. It's obviously very hand-wavy, and it's not going to get you to implementing a B tree, which, by the way, you shouldn't do. Right? There's good implementations out there. Critically, why is this important? Any database that stores its data in a B tree has several things in common. It has a certain complexity, typically O log n, for all of the common operations. It is designed for on-disk storage. The fact that blocks contain many, many, many items, and the fact that they're split and shunted off very rarely, means it is very good for storage media, relatively speaking. Because, as you might know, input-output, random input-output is expensive. You want to try and avoid jumping around inside of your data structure as much as possible, whether it's on memory, whether it's on disk, and whether it's on an SSD. In that respect, they're all the same. So this data structure minimizes the hopping you need to do at read time. It tries to minimize, or at least trades off, the amount of work you have to do in shunting bits around on the disk when you add data to the structure. But critically, it is optimized for reads. It tries to maintain very good read performance regardless of how much data you add to it and in what order. And this is critical because it sounds like a good thing, but it isn't always the right thing for your use case. Let's take one example. Let us assume the product that we're set to build is Twitter, right? Social network. Specifically, we're tasked with building the storage system for likes and dislikes. Right? You have a bunch of people coming in, reading tweets, liking, disliking if the social network allows it. And then you have various use cases for likes and dislikes. One of the most obvious use cases is sometimes you want to show the number of likes on a tweet. Right? You do that every day. You see that every day. It is a trivial thing. But more importantly, a like or a dislike is a signal to the back end of the social network for all sorts of things, right? If you're looking at like a discovery feed of tweets, how does the social network, how do Twitter know which things to show you on the For You tab, right? One of the signals they use is how many likes or dislikes a tweet may have. And those things tend to not be lookups, right? That's not a lookup. They're not gonna, Twitter is not gonna decide on a random set of tweets and then go look up how many likes and dislikes each one of them has. This is typically a batch process that happens on a lot of tweets, whether on a regular cadence, like a scheduled job, or whatever. The point is, it's not a lookup. It's a piece of data that they use in aggregate. What this means, in effect, is that a like or dislike, the sending of the signal into Twitter, is an extremely frequent operation. It happens all the time, right? Think of how many times you like a tweet or a Facebook post or whatever it is every day, right? You do that all the time. Conversely, though, when you consume that data, it is actually quite infrequent, and even more important, it is not critical that you're shown up-to-date information. If you're looking at a tweet, it doesn't matter if it shows you that that tweet has 29 likes or 30, right? That has no business ramification whatsoever. It is, however, critical that they be able to access that data effectively as part of the batch process. So the question is, are B trees a suitable storage medium for this type of data? It's obviously a loaded question. The answer is, it depends. It always depends, right? But for Twitter, it doesn't actually depend. It makes a lot of sense to look at it and go, no, we're making absolutely the wrong trade-off storing likes and dislikes on a B tree, because a B tree is inherently a read-optimized data store. And we don't read that data very often, right? I can cache in memory the number of likes and show you a stale number of likes for an hour, and you're not going to care. I don't need to go look up that number every time someone looks at the tweet, right? So I don't need a read-optimized data store. On the other hand, I do have a crescendo of like and dislike signals coming in from my however many users Twitter has nowadays. Let's assume 500 million just for kicks, right? I have 500 million people liking and disliking tweets. Well, there's no dislikes, so just liking tweets all the time. That is a massive influx of write operations, right? So B trees are just inherently not the correctly optimized choice, not the right data structure to pick for this use case. Writes are costly. Why are writes costly in a B tree? First of all, if you've paid attention, when you write data to a B tree, the first thing you do is you find the right leaf node, or at least the right node where the data is. That's a lookup, right? Just by virtue of wanting to find the right slot to put the number in, you have already made several hops into your data structure. You've already paid the cost of a lookup, and that is expensive. You also get write amplification. If I want to write just one 32-bit integer number into my data store, and it ends up taking a block and splitting it up, and that's a recursive thing, so it might end up taking further blocks and splitting it up, bits shuffling around my data store, that is a lot of write I/O for just adding one 32-bit integer to my data structure. And that's called write amplification. Now, it's not inherently a bad thing. It's a trade-off, and it's the wrong trade-off for our use case. And there's a question of wasted space, et cetera, et cetera. Critically, though, just looking at it, it's just the wrong data structure. It's read-optimized. We don't do many reads. It is heavy on writes. We do writes all the time. It will not scale as well as some kind of alternative structure. Now, it is worth noting, B trees are not a bad tool by any stretch. We use them all the time. Every index in every database that you could possibly mention right now that's even remotely like a traditional database is probably built on top of some kind of B tree structure. It's not a bad solution, but it's not the suitable one for this case. So I want to present you with a second algorithm for data storage that other databases use and which is useful for our purpose. And that is the log-structured merge tree, or LSM tree. Now, you might have heard, especially in marketing material for various newfangled databases, you might have heard of things like fractal trees and various other interestingly named data structures. Those are all variations on a theme. Basically, variations of LSM trees and variations of B trees are the two data structures used for data storage in pretty much any modern-day database system. Any other data structure is like a niche. It might be good, it might not. Things might change in 10 years. But right now, any database you'd care to mention is based on some combination of these two structures, often both for different use cases. So, what are log-structured merge trees? Fundamentally, a very simple concept. You have a server somewhere, the database server. You have a set of producers that send data into the database, right? You have just inserts. User 8 likes tweet 9, right? That's a signal. That's just one action coming in through the system. So these writes go inside of a memory buffer, often called the mem table, with timestamps on the keys. Now, I use timestamps liberally. Time is somewhat of an overloaded concept in computer science. Separate talk. There even is one. If you want, go Google, shameless plug, how shit works time, different talk. But besides the point, what's critical here is that for every write, right, you take in the key, you take in the value, you take in the now, the timestamp for now, and you put all of those in an append-only memory buffer. You just stick it there. Done. To start with. Now, obviously, in-memory storage is useless in and of itself. So, at some threshold, you decide that it is time to flush this table to disk. Now, the threshold is generally one of two thresholds, either time-based, right, because you want safety. You want to make sure that if a write happened against the database within a certain span of time, say 100 milliseconds, that data will have been flushed to disk. Or it might be based on load. How much stuff did I accumulate in my memory buffer? Past a certain threshold, that's too much stuff, I want to flush it to disk. How do I flush it to disk? I take that list in memory, sort it by key, discard older values that I don't care about. You will notice that the key C, okay, for value C, had appeared twice, which means one value is stale. I no longer care about it. I can just throw it away. I take the most recent values, sort it by key, and I just flush them to disk. This is a relatively cheap operation. Sorting is a little bit expensive, but not very. This is basically a type of merge sort, in effect. Now, once I have it on disk, it just stays there. It's totally immutable. Obviously, this isn't the whole story, but already you will be able to notice that any write operation coming into the server is handled effectively instantaneously. There are no lookups. It's just, give me a pile of bytes, I will find the right spot, and by find the right spot, I mean I have a pointer into memory or into disk where I write the next record, and I'm done. That's the write operation. So no lookups, no write amplification, no wasted space, no anything. Now, obviously, this isn't enough, right? This isn't a database system. We also need to consider retrieval and just the production viability of a system like this. So let's talk about the read situation. If I want to read the value of B, and I have a database server, it has some stuff in memory that has accumulated because I haven't hit that threshold yet. I have a bunch of those flushed tables that are typically called sorted string tables or SS tables on disk. And I get a query, right? A user wants to know what is the current value of B. Now, unlike with a B tree, where finding the value of B means finding the right position on the tree and just reading the value, here, what I need to do is I need to look at all of the stored stuff, because I might have B in memory, right? If I received an update for B within those 100 milliseconds, it might still be in memory. Or it might be on my initial SS table that I flushed, because I only ever got one write to B, and it was 2 years ago. Or it might be in any of the tables I've flushed since. In fact, it's likely to be in a few of them, because I don't circle back to previously flushed SS tables and do anything with them. They're always there, and I always need to take them into account. So the read becomes complex. Effectively, I need to look at every one of these tables, ask them, do you have a value for B? What is the timestamp for the value that you have? And pick the latest one, which can be in any of them. So I look at the mem table, no B. I look at all of these SS tables. I mean, if I find a value for B in the memory table, by definition, it's going to be the latest value, right? Because by definition, this is, I just stored the latest window into my state. By definition, it's the latest. Cool. Then I look at all of these SS tables. I find all of the different values of B with their respective timestamps. And only after I've looked at all of the SS tables and the memory table can I conclude that the value of B is 3 because that is the value associated with the latest timestamp. So this might seem incredibly wasteful, except for 2 things. First of all, I'm going to cover some optimizations in a second, and of which there are plenty. But before you think of this as wasteful, remember, this is a trade-off. There is no wrong answer in computer science. What are you trying to accomplish? This read operation might seem incredibly heavy because I have to look at several files and in memory, and I have to keep all that state in memory, blah, 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 blah. But if it happens very infrequently, who cares? That is not something you should care about if your read situation is rare, right? So depending on your use case, this may or may not be catastrophic. That being said, no database, no production database can really realistically live for an infinite amount of time. Data is being added more and more and more to this thing. It flushes SS tables to disk. Sooner or later, you're going to run into some kind of issue, whether it's you ran out of file handles, you ran out of space on disk, because you will notice the key B exists in 3 tables, just for this example, meaning I have a lot of wasted space. I don't need the old values of B. Those belong in the past. It might be useful, but it probably isn't. It's probably not what you care about. So there's a lot of wasted space here. To cover this, should have shown this first, right? I've been talking about this for the last minute. Right. These are some of the issues that we've just covered. Critically speaking, the differences are that the amount of I/O activity that you need for a read in a B tree is proportional to the size of the B tree. The more data you have in your database, the more you pay logarithmically, but still, the bigger your n, the more O of log n is. Here, the cost of a read is not proportional to the amount of data you have. It is proportional to the age of the data and how you manage the data in your system. Right? For a naive LSM implementation, one that never does anything with the SS tables and just keeps them forever and queries them on every read, the load of your reads is strictly linear to just how old your database is. Now, that might be fine. For the most part, it isn't. Right? So production databases actually have a lot of optimizations in place to both reduce the number of SS tables, get rid of unused data, and provide better ongoing read performance. So one optimization is Bloom filters. You'll notice that every SS table is a sorted list, basically a sorted set of tuples of key value and timestamps. It is very wasteful. You can do a binary search on it if you're looking for a particular key. But it is very wasteful to do a binary search if you can know ahead of time that the key just does not exist in that flush table. So Bloom filters are typically used as kind of a first-level optimization of, should I even look at this chunk of data? But more importantly, there is a compaction process. Every LSM-based database, through some kind of policy, and these policies can differ dramatically between database implementations, fundamentally, every LSM-based database runs a compaction process whereby it takes a bunch of older SS tables, effectively runs a merge sort, and that's exactly what a merge sort is. It runs a merge sort over a few of these SS tables, creates a bigger SS table to replace all of them, and then it can just use that SS table because the data is immutable, right? A query that runs on top of those 4 SS tables at the top is going to be semantically equivalent to a query running on that merge SS table on the bottom, except you get faster performance, less unused space, less wasted space, and all of these things that we've been looking for. So the compaction process can happen independently of anything else going on in the database. It can happen concurrently, and it usually does. And there are a lot of knobs you can kind of tweak to get different performance characteristics out of a database that relate to how often or based on what triggers compactions happen. We have these two fundamental algorithms, B-trees and LSM trees. Fundamentally, you would use a B-tree where read performance matters. If lookup performance matters more to you than how costly your writes are, you're going to use a B-tree style structure. A traditional database is often based on that. So that is why you would use MySQL or Postgres or whatever. Now, if you've ever heard expressions like, oh, Cassandra is really write optimized. Cassandra is really, really nice for writes. If you have a lot of writes, use Cassandra. And if you've heard of Cassandra, you've probably heard that statement because that's all that comes up, that plus the fact that it's really complex to operate. Basically, okay, the reason Cassandra is really, really good for write-heavy loads is because the underlying storage model for Cassandra is LSM trees. MongoDB also uses LSM trees a little bit differently. RocksDB I think they now work on fractal trees, but that is essentially a variation of the same idea. Right? So your traditional databases tend towards B-trees because that was what made sense in the 80s. Moreover, because traditionally storage was incredibly expensive. So you couldn't afford wasted space and you couldn't afford slack. And you didn't have the write-heavy loads that you have with modern internet-based web-scale products. You just didn't have that. LSM trees are not a new concept, but the implementations are relatively new, which is why you see LSM trees in more and more kind of NoSQL modern-day databases. Now, both solutions have their place. So, how do you choose, right? Circling back to the original question, you have a product. Your product is probably in the minimal viable product phase. You have no idea where it's going to go. You have no idea if it's going to be successful or not. How do you choose a database for it? Well, to be perfectly honest, it doesn't matter as much as you think. My recommendation is, regardless of what you're building, unless you know what you're doing, in which case this whole talk doesn't mean much to you, right? Take whatever you're comfortable with. If you have people on your team that are comfortable with Postgres, use Postgres. If you have people on your team that are comfortable with MongoDB and have built production systems on MongoDB, use that. Most importantly, if you end up owning, quote unquote, the servers, if you end up operating and managing your data stores on your own, do whatever your ops person tells you. If your ops person tells you, I am proficient in MySQL and I have never used Postgres before, don't use Postgres, use MySQL, because otherwise it's going to hurt. And the reality is that until you hit meaningful scale, your choice barely or doesn't matter at all. So go with what's easy. That being said, if you know something about what your product is going to require, if you know what your access patterns to the data are, like for instance, in the case of a social network, you kind of know what you're going to do with that data. You know that it's going to be very write-heavy and that you're not going to do lookups, then you can make a reasoned choice about which category of database you're going to pick. Now, there are a lot of different axes that you might want to consider, right? Which data representation is good for you? Replication strategies. Is it a clustered or a non-clustered database? Is it a managed product or not? All of these matter, but you can't talk about all of these in 30 or 40 minutes. So fundamentally, hopefully now you have a little bit more intuition about what the difference is between the kind of major players. There's obviously a lot more to learn, but I sincerely hope your main takeaway is start with what's easy and known, because it doesn't matter that much starting off. The more you know, the better choices you can make. So once you have some understanding of your operational concerns, of your data access patterns, your scaling needs, then you know which questions to ask. You can make a reasoned choice. Until that point, a little knowledge goes a very long way, and I hope you have enjoyed this talk. Thank you very much. So 45 seconds doesn't leave a lot of time for questions, does it?
No. Actually,
Okay,
I had one myself, but maybe I'll do it offline.
Okay, feel free to catch me outside. I'll be very happy to answer any questions or argue, whatever it is. Thank you.